Okay, good morning, everybody. Hello, can you hear me? If you can hear me, smash that chat button. Let me know if I'm coming in loud and clear. Hello, everyone. Hello, thank you for the reactions. So great job from Bill Ellis. As I said before, Bill is a qualified pilot, and so he flies planes and all sorts of interesting aircraft around, which is pretty amazing. Yes, thank you for smashing that chat button, Snea. Um, Good morning to everyone. So yeah, Mario's on break at the moment. I've got a couple of new friends here. If you know who's behind me, let me know in the chat. Mario will come back though. Don't worry. Don't worry. So week 2, can you believe it? Week 2 already. Week 1 is just flown by. I hope week 1 was good to you, and I hope you're getting settled in. Okay. So in today's lecture, we're going to continue our journey into limits. And the purpose of today's lecture is to look at limits in a bit more rigorous detail. Okay, so we're going to be a little bit more careful about how we define what a limit is and how we work with them. So last week we talked a little bit about limits, but it was mostly just algebraic manipulation, right? So we're going to do something a little bit different today. So let me share my screen with you. Da, 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 da. Okay, so this is part 2. Okay, and we're going to look at more rigor and detail. Okay, so that's the idea today. So we'll be carefully defining what we mean by a limit, and then we'll be using some definitions to work with certain problems and formally prove that limits are equal to some value. Okay, so this is the first thing that we're going to discuss. You probably haven't seen this at school, so I suspect for many of you this is a new concept. Okay. Yeah, Nicholas, we did look at limits last week, but the questions were quite easy, and we were mostly looking at algebraic manipulations when you have a limit question, right? But this is different. It's a formal definition. Okay, and I think this will also be this will sort of be new, but there's no formal definition. So this is up here, we're approaching infinity, and down here we're approaching finite points. Okay, so let me show you. So formal definition, limits as we approach points, and some basic examples. Now, I want to leave this blank because I want to draw a picture here. So I'll come back to this slide in a minute. But let me start with this formal definition. And I know you've just had an hour of algebra. So this, you might be tired or a bit sick of maths at the moment, but this is a super important concept. And in fact, in your Mobius tutorial that's due today, you would have briefly had a look at this, but we didn't discuss it in lectures yet. Okay, so now is that opportunity to discuss it in a bit more detail and make some sense out of it. Okay, so when we use this kind of notation, mathematically, what does this notation even mean? Well, last week we talked about a horizontal asymptote, right? So y equals L was a horizontal asymptote, and the function was approaching that asymptote as the input got large and positive. Okay, now up here, this is a slightly more formal definition of what this actually means. This is a more mathematical definition. Okay, so L's a number, F's a function. If for every positive value of epsilon, there's a corresponding m, so m depends on epsilon, such that this is true, then this is what we mean by the limit of f of x equals L as x approaches infinity. Now, we've got some inequalities here, and there's some Greek letters, and it's not really clear what this is. So let me draw you a picture, and I'll try to show you what it means. Okay, so don't freak out. There's some inequalities there, but drawing a picture can really help. Okay, so what we're trying to do at the moment is to understand what it means, and then we'll move on to actually solving the problems. Okay, so what do these things mean? Over here, that's just the distance between the graph of the function and the limit. Okay, so what does this mean? This distance is small whenever x is large. Okay, that's how I remember it. The distance between the function and its limit is small if or whenever x is large. So let me draw a picture, and I can show you. Now, don't freak out. This takes time to learn, right? This takes time to learn, and even really great mathematicians took probably hundreds of years to really understand this. Okay, so I'll put this in here. All right. So let me just draw a picture. Okay, so there. All right, so that should be enough. So here are your axes, right? And I've got a number L. And in this picture, it's a positive number. Okay, and I can draw a little horizontal line there, horizontal asymptote. Okay, what I'm going to do is I'm going to draw a little band around that horizontal line. Okay, so I've kind of got a horizontal strip here where this dotted line is like down the center. Okay, so what happens is, let's say here's my graph. The graph eventually, as we move to the right, gets into this band and it stays there. Okay, so in this picture, this could be a value for m here, because if I go to the right, then my graph stays within this green horizontal strip. Okay, now for the limit to exist, this has got to work for every horizontal strip. So I can squish it, I can pull it apart, and you still need to be able to find a point where it enters and never leaves. Okay, so that's essentially what it means, right? You've got this horizontal line, you draw a strip around it of width 2 epsilon. The graph enters the strip at some point, and after that point, it never leaves. It never leaves the strip. Okay? Now, if this strip is really thin, then you probably have to go further to the right to get it to stay in the strip. If the strip is really fat, then you can probably come over here, right? And m's not so large. But this is what it means. Okay? This distance is small when x is large or large enough. Yeah, Abdul Rahman. So epsilon, it has to work for every epsilon. Okay, so you can see here in the definition, if for every positive value of epsilon there is a number m such that this is true, then the limit equals L, right? So so I'm just drawing a picture with a specific epsilon, but It has to work for every epsilon. Okay. All right, so a few questions in the chat. So Snea, instead of saying the function gets near L, we give it a strict boundary, right? Yeah, so usually what happens is if and we'll see this in a minute, when this strip gets really thin, we have to go way out to the right. Okay. Yeah, Matthew, that's a good question. Out of curiosity, why is the formal definition of a limit in Mobius under week 1? If you had a look at the last question, Matthew, it says very clearly up the top of the Mobius thing that this is preparation for week 2. Okay, it's preparation for this lecture. So hopefully that makes sense. Yeah, Alberto, you're absolutely right. The final product will be an M that works for every epsilon. That is exactly right, Alberto. I couldn't have put it better myself. So the idea here is to find or actually construct a M that works for every positive value of epsilon. Okay? So that's for you, Alberto. Okay? So let's do an example. Okay? Let's do an example. So you're wanting to construct an M or an find an M such that it works. Okay, here's an example. So you'll see that there's a definite pattern with these kinds of questions, and we can deconstruct them and see what's happening. Okay, so the limit is obviously 4 for this question. We did some of these questions last week, remember? So what you can do is divide the top and bottom by the highest power in the denominator. Oops. Okay, so you can put this in here. So that'll be 8 minus 3 on x all over 2 plus 7 on x. So what is this going to go to? This will go to 0 as x becomes large and positive. This will go to 0 as x becomes large and positive. So it's going to be 8 on that. Oh. Okay, that goes to 0, that goes to 0. So you're going to get, okay. Yeah, Nicole, we'll do an example, like what M is right now, okay? So M's just a value on the x-axis, okay? So you can see in this part, we're actually going to find a particular value of M, all right? All right, so that's easy. This is what your L is going to be. We could work that out. So prove this from the formal definition, okay? So now it gets a little bit harder because we want to show that we can actually find an M such that this is true, okay? So the idea is to start with this left-hand side, simplify it as much as possible, and then solve an inequality. Okay, so that can be part A, part B. All right, so let's consider this. So basically, I'm just starting with this left-hand side of this inequality, okay? All right, so here I've got this 8x minus 3 over 2x plus 7, and the limit is 4, okay? So what I'm going to try to do with this is simplify, use this inequality to find what M is going to be, okay? So as I go through, you'll see you'll see what happens. I'm trying to simplify and then solve an inequality. They're probably the two most important steps. Okay, so let's put this all over one denominator. So that times that will be 8x. That times that will be negative 28. And I'm going to get something like this. Okay, now you can see, well, that's going to cancel with that. Oh, sorry, with that. Okay, so that's still here. And I'm going to get negative 31 on the top and that on the bottom. Now see what I've done here. I've split up the absolute values into top and bottom. All right, so the absolute value of the top is just 31. And what I'm going to do with the bottom is the following. So James, I just multiplied 2x by negative 4 and 7 by negative 4. Okay, hopefully you can see that I've just gone that times that times that, and you can put them up there. All right, so I've got that pretty simple. What I want to do now is simplify this. Okay, so what I can do is go, bam. Okay, now here I'm going to make the assumption that x is positive, right? So this is like an inequality here, and you can say, okay, 2x is less than that. Okay, and so when you divide, you can reverse the inequalities. Okay. All right, so now we started with something very complicated, and now we've got something really simple. So what I can do now is go, right, I really want to solve this thing over here. Okay, and what I can do now is go, right, 31. When will this be less than any given epsilon? How big does x have to be for this to be true? Okay, so I'm doing that, less than that. I've taken a new line. And it's very easy to do. Bring the x up there, bring the epsilon down there. Okay. Okay, so all I've done is I've put the x up there and the epsilon down there. I know x is positive, okay, because I assumed it there. So what's this? This, oh my goodness, is your m. All right. Forrestook, you don't need to eliminate the 7. I've just done it because it's easy. It's an easy. This is easier to solve than 2x plus 7 in there. Okay, I've just done it because it's easier. You don't have to. You could stop there and go, well, let's manage away the absolute value signs and solve 31 on 2x plus 7 is less than epsilon. But this is actually even simpler. Okay. No, Max, there's like one of the strange things about these questions is there's a million different answers for m. There's not just one answer for m, right? There's a million different answers. Okay. So yeah, so that's fine. All you need to do is find one m where it works for every epsilon, right? So this m can take many different forms. Okay, and this is a really simple one. Yeah, well, I mean, the reason I'm eliminating 7 is because I want to solve something that's easy to solve. You know, I want to solve it because it's easy to solve. Okay, so a couple of things. The m here is not unique. You can have lots of different m's here, right? But it has to work for every epsilon. Let's do an example for that was asked for part C, and this will probably give it some concreteness. Okay, so if epsilon is 1 on 100, what is the corresponding value of m? So all we would do is go here and put in epsilon equals 1 on 100. Okay, so here you're going to get 31 divided by 1/50th, which is 1550. Okay, so what this means is if you want to get into your strip, and the strip has width 2 on 100ths, you have to go all the way out to 1550 to get and stay into that strip. Okay, so to get this less than 1 on 100, x has to be bigger than 1550. All right. So that's a lot of algebra in here, but the idea is usually the same with these problems. Work out the limit using elementary methods, right? To do the proof, you start with that and you want to simplify as much as possible. Part of the simplification involves removing the absolute value signs, okay? And then somehow getting down to a simple inequality that you can just rearrange to solve. Okay, you can see here the m that I've chosen is, well, it's going to be positive anyway, but this is one m that will work for every epsilon. And here's a specific example. Nicholas, I'm solving that. What I want to do is find that, solve that for when x is large enough, because it comes up from here, right? So that's there. I've got that less than that. So if I solve this for less than epsilon, I know that's got to be less than epsilon because that is smaller than that. Okay. So it's a good question. Let me go back to the picture. So that would be, okay, for this particular problem, Nandan, that would be 4. That would be 4 plus 1 on 100. That would be 4 minus 1 on 100. And this would be 1550. Okay. So for this one, for the very last one, we're taking an example where epsilon is 1 on 100, L equals 4, because that's the limit. So that's what you get. That would be 1550. Okay. All right, so let's draw a picture. I'll do some GeoGebra with this one because I think it's important to actually see what's happening. So here is our original function. If I zoom out a bit, you can see it looks like it's an increasing function, but as x gets large and positive, we're heading off towards 4. Yeah. And then what I've done is, actually, I don't have it in this graph. I'll save it for the next one. But definitely the graph is 4. And if we go out far enough, okay, out here, then we can always get into that little band that contains the limit. Okay, but for the next example, I'll give you a few more graphs here. Okay, so I'll come back to that. Okay, so let's do another one. Hopefully you can realize a pattern now with these kind of questions. Find the limit, then prove it using inequalities. And then they might ask you for a specific value of epsilon and m. Okay, So let's do another example. Now, don't worry if this doesn't seem like you're understanding it straight away. These are quite complicated ideas and they're quite complicated problems. So what you want to hopefully do is to be able to solve the examples, but also to have some idea of what's going on as well with the theory. All right, who can tell me in the chat what, if I take the limit of this function as x approaches infinity, what is the actual limit? Yeah, it is 0, okay? So I won't concentrate on that too much, right? You've basically got a huge denominator and a numerator that's bounded between -1 and +1. So the denominator drags this thing down, okay? So if I show you a picture, it just gets dragged down to the axes, okay, to the x-axis. But the most important thing here is proving this from the formal definition, okay? So you can see in the previous example, we started with this, we simplified, got rid of the absolute value signs, and solved an inequality. We're going to do pretty much the exact same thing with this one, okay? But it's just a different function, okay? So let's do part B and spend some time on that. Okay, so this is going to be this. All right, so what we would like to do here is remove the absolute value signs and simplify as much as possible. Okay, so the first thing, obviously, this is not going to change anything, having the 0 there. Okay, so can we form an inequality on cosine x? And the answer is yes. We know that this is true. And so this is also true. Okay, this is true for all x. So one thing that you can do here is go, right, I can simplify this in the following way. All right, this is very, very common. Now, can we simplify this bottom bit? Well, we can. I'll go down here. And one way to do it is to say, okay, well, the e to the x is complicated. The 7x is pretty simple. I know that e to the x is always bigger than something like this. Okay? Right? And so when I flip those, I can say, okay, this is less than this. And I'm going to, again, assume that x is positive here. Now, the nice thing about this is I can just say, right, that's just 1 on 8x. So I've got a very simple expression here. And just like I did in the previous example, I'm going to move that over, solve the inequality involving epsilon, and form an m. Okay? So I just bring the x up there, bring the epsilon down there. Okay? You mean from Shub? You mean from here to here? Or it's up here, right? I mean, you can put a greater than or equal to there if you want to, but I'm not going to do it, right? I mean, you can if you want to, but you don't have to. I'm just being a bit more precise. Okay? If you want to keep it, you can keep it. Right? You're still correct. Okay? So we have this, we solve this, and oh my goodness, that's your m. It's going to be positive. Okay? So we kind of followed the same process as before, we just had a different setup with our x's and functions and stuff. Okay. Nicholas, like divide both sides by epsilon and multiply both sides by x. Okay. So do you mean going from this step to this step? Okay, so what I'm trying to do, right? So I've got this less than that, right? And I want to basically show that this distance is less than epsilon, right? So this is less than that, and if I can make that less than epsilon, this thing's got to be less than epsilon. Okay, it's a really good question. So this is less than that. If I can make that less than epsilon, this has got to be less than epsilon. All right. So that's a really good question. Okay. Yeah, it's a really good question. Yeah, Joyce, you could do that. Joyce, you could do that. You could like that's a really good question, Joyce. So you could, if you wanted to, have a different inequality here. Okay, you could, if you wanted to say, right, e to the x is always positive, so this is less than that, right? Not a problem, Joyce, not a problem. Okay, in fact, I like your solution because it's even simpler than mine. Okay, so yeah, you could definitely do that. So let's do that. Let's do the Joyce solution. Right? Alternatively, right? You can go with, yeah, you could do that. And again, we'll say that x is positive here. Okay, and then you would just solve this. Okay, so that would be your m for this one. So you can see how there's lots of different m's here, right? So this is the Joyce solution, which I like because it's even simpler than mine. Okay. So let's go with B. For the value of epsilon equals 10, what is the corresponding value of m? So I won't do the Joyce solution here. I can just go here. So if epsilon equals 1 on 10, then m. Okay, so you just put it in here. So it's going to be 1 over 8/10, which is that. Okay. Yeah. Okay. CZ Chan, you've got to find an m that works for every epsilon. So you're finding the m. That's what you're supposed to prove, right? You've got to construct an m such that this is true. Okay. Yes, correct. CZ Chan. Exactly. You've got to prove that there exists an m, right? Yep. Okay. This was our m. This was our m. All right. Now, like I said before, don't worry if this seems very strange and different. It's one of the hardest problems in the course. Okay. So, my advice, don't freak out. Okay. Don't freak out because this is quite difficult mathematics. Okay. And there's two things to think about here. One is the concept of this epsilon m limit, right? What does it mean? And the second thing is, how do I solve the problems? Okay. So what you would hope to do is be able to do both. but it takes time, and you really need to think about, what does this mean? What does this mean? Do I have an M? What kind of inequality should I use here? Okay. Yeah, Alberto, the absolute value signs is important, to simplify them. Essentially, many times you can just simplify them by assuming that x is positive. Okay. Yeah. Leslie, good question. What if my answer is far from the answer? Leslie, well, I don't know what you mean. The answer in the back of the book may not match your answer, but you may both be correct. Okay, this is one of the things that frustrates some students. There's more than one answer for these kinds of problems. Okay. So Tom, good question. What does the M positive mean? It means that basically, in this picture, the M is always on the positive x-axis. Okay, so I'm basically just saying that to say, right, over here I assumed x was positive, and here x is still positive. Okay. Yes, Snaya, I think I did here. Yes. Okay. That doesn't change as long as your M is big enough. It doesn't. You don't need the smallest M, right? You just need an M that works. Okay. All right, Farhan. Exactly, Farhan. You've summarized that perfectly in the chat. Basically, we're messing around with the inequalities in order to simplify, which involves substituting in simpler and simpler equations. Okay, absolutely correct. So let me show you what's happening here with the graphics on GeoGebra, right? So this is it's a bit hard to see, but this is the f of x minus L for our one, right? And what I've done is I formed an inequality on the cosine x. Okay, you get something like that, which is a little bit bigger, that green function. I've simplified that using that function. Okay, you can see all of these functions go to 0 as x gets large and positive. Okay. Now Joyce's suggestion was just 1 on 7x. That's also a good example. Okay, but this is what's happening. You're using these inequalities to simplify the mathematics when you solve your inequality to find m. Okay. All right. Tom, because the m is not unique. The m, okay, so it's a really good question. Let me show you on my screen. Okay. This is one m. I can choose an m here, or an m here, or an m here, or an m here, or an m here. They all work. This is just the smallest m. Okay, that m would work, that m would work, that m would work. So they all work. They're all correct, and they all work. Okay. Part C depends on your choice of m, Tom. So for your the m comes from part B, and it could be lots of different things. So based on part B, you'll get an exact value in part C. Okay. All right. I'm loving these questions, but let me Ava, there is a smallest possible value for m, but it's quite difficult to find sometimes, and it's not always easy to find. Okay. All right. So let me move on to the next part of this lecture, which is approaching points. So we've been approaching infinity, and we've been formalizing that. But now what we want to do is basically approach points. So you've got a finite point here, and you approach it from the left and from the right, and you ask what is happening with your graph. Okay, so the kind of notation that we use is this kind of notation. Okay, so here A is no longer an infinite thing. It's just like 1 or 2 or something like that. So it might be something like this. And you'll be pleased to know that for this setup, we're not going to talk about any epsilons or formal definitions or anything like that. Okay, we save that kind of stuff for when we approach infinity. With this stuff, it's much more straightforward. Okay, it's much more straightforward. Okay, so the same ideas apply. We want to know as we approach some value on the x-axis, what is happening to the graph. Okay, does the function approach a particular value, and what is the value? Okay, all right, so some notation. When we write this, we mean as we approach a point A, the graph approaches some value L. Okay, so when we write something like this, it means that if I'm approaching positive 2 from the left and from the right, it means that, sorry, 1. It means that my graph is approaching, say, 2 here, right? Okay. We have a right-hand limit and a left-hand limit. So this is, if we're on the right-hand side, that's written a plus or 1 plus, I guess I'll put it here. And if we're on the left-hand side, then we write it with a little minus sign in the top right-hand corner. Now, an important idea. If both limits exist and are equal, then their joint value is denoted by this. If they're not equal, then the limit doesn't exist. Okay? So that's a really important idea. If the left-hand limit and the right-hand limit are both equal, then their joint value is written as this. If they're not equal or they don't exist, then we say this general limit does not exist. So the best way to understand these ideas is through examples. So let's have a look at some examples. Okay. All right. So here's a pretty simple looking example, right? We can simplify it in the following way. And as long as x is not equal to 3, I can actually cancel off these things, right? So the graph is, the function is not defined at x equals 3, but it's x plus 3 everywhere else. Okay? All right, so let me draw a little picture and we can work out the limits. So let's make that 3, and I'm going to go there. Okay. So who can tell me if I'm coming in from the right, what is this function approaching as x approaches 3? Can anyone tell me in the chat? So as x approaches 3 from the right, what is happening to this function? Okay, some people are saying 3, some people are saying 6, some people are saying 7. So here, the 6's are correct, okay? So limit as x approaches 3 from the right of f of x, well, just going to be 3 plus 3. All right, what about the other side? What's going to happen there? Can anyone tell me? What's that going to happen? So it's still 6, exactly. Thank you. Okay, because as we come in here, the graph is going up, 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 and it's approaching 6 as well. Okay, so we know that these two values are equal. And as James has said, the joint value of these two will be this limit here. Hooray! Now, notice the function isn't defined at x equals 3, but we don't care about that with the limits. The limits still exist, even though the function is not defined at x equals 3. So that's a bit weird, right? Sneha, no, the function isn't continuous at x equals 3 because it's not defined. It's undefined at x equals 3. So it cannot be continuous there if it's not defined there. Okay, it's a really good question though. So what we did there, we simplified the function. We obviously knew that x can't equal 3. We drew a picture and came in from both sides. They were both equal. The joint value is the limit. Okay, so that's kind of some of the examples you'll see in your Mobius quizzes this week. Okay, so that's a bit. You just need to be careful there. That's all. Just need to be careful. Now there are of course some easy situations where you can just plug the numbers in. Okay, so yes, Sneha, exactly. We don't need to worry about what happens at 3, x equals 3, right? We don't care about that. We just care about as we get really close to it, what's happening. Okay, so in these ones, these are super easy because there's no division by 0, there's nothing different or odd going on. So all we can do here is put in your values. Okay, same with this one. Okay, so this will be 8 over 3. Yep, this is super easy. Okay, Super Mario easy. Okay, so just remember, these ones are easy. These are the ones that you see at high school or whatever. Sometimes you can evaluate a limit like that. Super easy. Okay. Oh yeah, except when you make a mistake. Oh. Ah. Mamma mia, mamma mia. Made a mistake. Sorry, that's an epic fail. Anyway. Ah, all right. So easy. So you will see some of these questions in this course. All right. Visual question. Who can tell me from the graph? Now, this is a really good question because sometimes you're given these graphs. You don't know what the function is. It's just a graph of a function. What are these limits? All right. So who can tell me what is the limit as we approach 4 from the left? Can anyone tell me? Yeah, So you can see here the graph's going up, up, up towards 2. All right, thank you. And what about if we approach 4 from the right? Yeah, Nicole. It's going down, down, down towards towards 1, sorry. So who can tell me, does this limit exist? Yes or no? Okay, so it does not exist. Oh, they're having an existentialist crisis. What about this one here? So Abdul Rahman, so it's a good question. The graph is coming down and you can see over here, that's what it's approaching, 1 on the horizontal axis. Okay. But when we come in this way, the graph is going up towards 2. All right, so what is this? 5. Yes, it's definitely approaching 2 from the left and 2 from the right. So no, f of 5 isn't defined. Okay. So Nicole, the limit doesn't exist because these two numbers are not equal. Okay. For this limit to exist, this and this have to be equal, and they're not. Okay. So the left-hand limit and the right-hand limit have to be equal. All right. Last one. Let me do this. I'm going to do this on GeoGebra. Okay. So here it is. You've got this function here, and you want to work out the left-hand limit, the right-hand limit, and the overall limit. So let me show you a picture. Oh, it is defined. You're right. Thank you. Thank you, Matthew. So it is defined. I didn't see the jump up there. Okay, so that's not correct. All right, last question. I'm just hurrying now. Plot this function. What are these limits? Okay, so let me just quickly show you GeoGebra and then we can finish up and I'll be happy to take your questions. Like I said before, don't worry if the epsilon stuff at the start was quite difficult. This is this function here. So who can tell me on the chat, what is the limit as we approach 5 from the left? Okay. What is the limit as we approach 5 from the left? -1. Exactly. Thank you. And what is the limit as we approach 5 from the right? +1. So does the limit exist? Okay, let me go back here and I'll just share my Chrome tab one final time. So this was -1. This was 1. They're not equal. This does not exist. Okay. Now you can do algebra to simplify that, but I've just done it quickly. Okay. So these one-sided limits are fine, but this more general limit does not exist. Okay. Yes, Stephen. So it's a good question. Limit as x approaches a is the joint value of the left-hand limit and the right-hand limit. Okay. So this is actually the joint value of that and that, but they're different. So this can't exist without both of these being equal. Okay. So we call this a left-hand limit, we call this a right-hand limit, and we just call this the limit. Okay, so this is like a left hand limit. This is like right hand limit, and this is just limit. Oh, okay, everybody. Sorry, I went a bit over time. The epsilon stuff is difficult. Okay, the epsilon stuff is difficult, and look, don't worry if don't worry if you are having trouble with the first part of this lecture. It's complicated, but the way you get good at it is practice. Try to draw pictures where you can and look for strategies. All right. So we've got a couple of minutes. If people want to say hello, turn their microphones on, post some questions, I'll be here for a couple of minutes. So just let me know. People can speak if they want to. You should be able to speak. Okay. So let's have a look. Dijant. If the left-hand limits and the right-hand limits exist, then yes, the limit exists. And they're both equal. Okay, so if the left-hand limit and the right-hand limit are equal, then the limit exists. Okay. All right. So what else have we got here? Shub, the office hours have just been posted on Moodle, so go and have a look there. Anubhav, thank you. Thanks for coming. I know 2 hours of mathematics in a row is long. Thanks, Azur and Alyssa, Ava, Heidi. Thank you. Yeah, Omar, it's a good question. I can show it to you algebraically. That's not hard to do. So I can show that to you now. So what you can do, basically, it's just managing away the absolute value sign, right? So you can say it's x minus 5 when x minus 5 is greater than 0, and it's that when x minus 5 is less than 0. So this is 1, this is negative 1. Okay, so this corresponds to x greater than 5. This is x less than 5. Okay, so now you take the limit of that, that's always going to be 1. Take the limit of that, that's always going to be negative 1. So that's where these two things come from. Okay. Okay, Omar, so that's pretty, it's just simplifying the function, really. It's just algebra. Okay. All right. Oh yeah, Abdul Rahman, 2 hours at 2 a.m. is even longer. I know, buddy. It's hard, right? Thank you, Eloisa and James. Jason, who? So Dijan, so the answer is limit won't exist. Hang on, no, sorry. Let me say that again. The left-hand limit equals the right-hand limit. The limit exists. Okay. The value of the function doesn't matter. Okay. It doesn't matter. It will later when we talk about continuity, continuous functions and stuff. But right now, doesn't matter. Okay. All right. What else have we got here in the chat? Oh, Bill says he has an office hour now. Okay. All right. Okay, everybody. I might see you at the tutorial today. It's on, I think, at midday. So if you want to come and say hello, feel free to come and say hi. Yeah, it's on midday Sydney time. If there's no further questions, oh, Nicole, I have a question about the page before. Okay, let's go back to the picture. It's a good question. Okay, so let's go there now. All right. So Nicole has a good question. I have a question about the page before. Why is the limit as x approaches 5? It's not. Okay. So, oh yeah, no worries. So as we approach 5, the graph is going towards 2 from both sides. Okay. All right. Correct, Nicole. Left and right hand limit are both approaching 2 as we approach 5, right? So that's what this means. Yeah, Ethan, the left and right are not equal. Does the function have a limit? No. The answer is no, no. The limit doesn't exist. Okay. That's correct. F of 5 is up there, right? That's the value. If you go to x equals 5, it's full. Yeah. This has got nothing to do with the limit here. I'm just saying that the limit and the value of the function aren't the same. Okay, at 5. Yeah, Yoshi. He loves the calculus. All right, folks. Maybe I'll see you at 12. Yeah, Colleen, yeah, it's helpful. It's not necessary, but it's helpful if you want to solve the problems, right? It's helpful. So what you try to do is simplify it and get a bigger function that's actually simpler. Okay. So I think to me it works really well, but it's hard. Yeah, Dijan, I take 3 tutorials a week, 1 today and 2 on Thursdays. Yeah, Colin, if it's lesser, then it's not useful. It's a good question. So you don't want to choose something that's lesser than the original expression, because it's just not going to give you what you want it to give you. Okay, folks, time for a break. See you later. Enjoy. See you on Thursday for the next lecture, and yeah, have a great day. All right, bye everyone.